To start the morning session of today. So it's a pleasure for me to introduce Sijue Wu from the University of Michigan, which will talk about the time behavior of the water wave.
Okay, thank you very much for the invitation. I would like to thank the organizers for the invitation and for the very nice time here. Okay, so what I'm going to talk about is a more recent work. So the main concern is still water wave. Okay, so the main concern is following. Say, for example, we have, so this is a wave, right, water wave. And of course, very often, like if you go to the beach, you will see that's what you see, right? So there's a button like this, okay, and we call the button, let's say, called Y, okay, and the water wave, it's gamma T, okay. Am I right? Something wrong with what I write? Okay, so don't worry. Okay, so this is a water region, right? So this is a typical thing, like, for example, if you have water in, in the bathtub, you always have a boundary, okay? And then you always have the wave interact with the boundary. So the question is really how the wave interacts with the fixed boundary. Okay, so gamma, fixed boundary. And this gamma T is the free surface. Okay. So the question is, how do we understand interaction between the fixed boundary and the free boundary? Okay. What? That's right. That's right. But of course, before I continue here, let's review some historical result. Okay, so what is known? Okay, so of course that's the wave we often see in the middle of the ocean, right? So that's really far away from the boundary. And from what I draw, I don't even draw the bottom. Okay, so this means really in the middle of the ocean, and the bottom is very often neglected. And you can also have a bottom. Okay, so this is the work we were working on like 20 years ago. So we assume that the density of the air is 0, the density of the water is 1, and there's a free surface, and the fluid region is omega t, right, and there's a gravity, okay? And we assume that the water is inviscid, incompressible, irrotational, and the surface tension is neglected because we care about the motion of the large wave, right? So surface tension is responsible for small wave. We just neglect it, and there's a gravity. And we assume the air density is 0, so that means we will neglect effect of the wind, okay? And so the question is, what are some typical behaviors of water wave, okay? And very often, we care about the so-called well-posedness, okay? So this is the motion of the fluid, and we know that it's described by the Euler equation. And we have divergence free. This is incompressible, irrotational. And because the surface tension is 0, so the pressure is 0. So the same thing works here, right? So the pressure is 0. Okay, I have the same equation, except I have to specify one more thing. Okay. Okay. Divergence is 0. Curl equals to 0. And this is in the fluid domain. Okay. And then I have pressure equal to 0 on gamma T. And this is free surface. But on the fixed boundary, we know the velocity it can slip, right? But it cannot go inside the fluid. So this is on gamma. Okay. So that's the equation in this if you have a fixed boundary. So this fixed boundary, of course, doesn't have to interact with a free surface, right? It can be like it can be free surfaces like this. This is gamma T, okay, and this is a fixed boundary, okay, gamma, okay. It doesn't have to interact. Of course, it can interact, okay. Okay, so what do we know about the you have B what? Okay, what did you say?
If you write the Euler equation this way, may I suggest that don't call curl V equals to 0 in this simple equation, curl of V0 equal to 0, and its conclusion.
That's right.
Otherwise it's over the curl.
That's right. That's right. I should say one more word that it's well known that if it's for Euler equation, if it's initially irrotational, it remains irrotational for all time. It's not assumption on the solution. Yeah, okay. So this is really.
That's what I mean to be pedantic.
Okay, I see. Okay, sorry.
Unless there is an intersection like air.
Okay. I don't know. Let's see. Okay. Okay, so let's see. But this is Euler equation, right? So this is Euler equation. With an intersection like that, we are not sure. Okay, so leave that out for a moment. So we know that if in case there's no surface tension, there's a very important condition. It's called Taylor condition. And the Taylor sign condition basically requires that the pressure, this N is outward normal. So that means this is inwardly the pressure should be really increasing, right? So if it's decreasing, there's a force rip open the fluid, and then there will be air bubble forms, and this formulation will be ill-posed, right? Because in this formulation, it really assumes that there's only one free surface and should be no free surface to form inside the domain, okay? So if your pressure is ripping open, and then there will be new bubble inside, so you have to reformulate, so it's ill-posed, okay? Okay, so for this condition, and this was posted by, proposed by G.I. Taylor when he studied this not simplified. So this like the almost flat situation, right? If the water is above air, and then he calculates and he finds that negative dPdN is negative, and we know this situation is not stable. And if air is above water, we know this is a stable situation. In the almost flat situation, you can calculate it as to be positive. So he proposed that this should be really the condition that keeps the stability of the free surface. Okay. But what we know is the following. Okay. So the old result is following. So there's no bottom. Suppose there's no bottom, absolutely no bottom, okay, no interaction. Then the time set, and suppose that we're only working in the region that the free surface is like C2 or better, right? So more smooth. Then the Taylor sign condition always hold, actually with a strictly lower bound, C0 greater than 0. And we can solve the equation for a short time for as long as the free surface is non-self-intersecting. And say, suppose initially the free surface in HS, S is greater than 4, and then it remains in HS for a short time. Okay, so you can have a short time existence and uniqueness. Okay, and actually this fact, this is the second proof. It's not the first proof we had in the very first work. Actually, this result holds for both 2D and 3D. Okay, so after we know that this actually is a fact, it's not difficult to prove. So I just used this proof. And this proof is just gotten by just applying divergence to both sides of this equation. And because this is curl-free, and then you get Laplace P plus gradient V squared equals 0. So Laplace P is negative gradient V squared is less than or equal to 0. And then you use maximum principle, you get greater than or equal to 0, right? But you do have a lower bound but with some further work. Okay, so I'm going to, if I have time, I'm going to talk about it with the other proof because, okay, so, and this condition, of course, there's some historical result that was proposed much earlier in the earlier work of Tom Beale, Tom Ho, Lowengrub, and this is where the importance of this condition came into mind of everybody, that they show that if you have a solution which satisfies this Taylor sign condition, if you linearize about the linearized equation about this solution, then you have linear well-posedness. So this sign, so the importance is already there, but now we can prove it's actually always true. Okay, and the earlier work, there was some earlier work for small data. So this means that this wave has to be almost flat. Okay, it's not arbitrary wave. You cannot overturn. You cannot. But so right now that's the result. Actually, your wave can really overturn like this. Okay, this is also well posed. Okay, and this is well posed. Actually, is not surprising, right? Because this is really the reason why you can surf, right? Because a surfer can surf because this surface is smooth. Okay, so they can stand there, and the wave is not going to clap on top of them, so they can surf. Okay, so this is really this Taylor sign condition means. Okay, and then there were a lot of more additional further work, further development since then was for local well posedness. So, for example, you can also include surface tension, and we know surface tension has smoothing effect. Okay, so you can also include a button, but this button doesn't interact with interface. Okay, so this distance, it's like this one. So this distance has to be strictly greater than 0. Okay, so this distance we call h has to have a strict lower bound. Okay, and then you can also solve for a short period of time, and you can also include a vorticity initially. But then, of course, the vorticity will evolve, right? There's an evolution equation for the vorticity. And you can also solve for a short time. But the key point is really, in all of these work, you have to assume negative dPdN is strictly greater than a constant. Okay, it's greater than a strictly a positive constant. So in all of these work, that it's crucial that the negative dPdN is greater than a positive constant. Okay, but in those work, because you cannot really prove it, you have to assume it. Okay? Because the bottom, the vorticity, and the surface tension all indicates that it's no longer, because here it's important, right? Because you just get Laplace piece that, right? If you have vorticity, you won't have this equation. You have a positive term there. And if you have a bottom, the equation, it's not clear what's there, right? So actually, we have a formula shows that for certain type of bottom, the negative dPdN can be negative, okay? And if surface tension, it's also not clear, right? Because everything is important. P equals 0 on the boundary is important for the negative dPdN is greater than equal 0, okay? Okay, so, but there are also results. Okay, so I'm not going to talk about large time behavior, the global existence. I just mentioned the recent work. So the recent work, so we also know there are quite a few work now on the global existence for small and smooth initial data. And for example, in 2D, and we have that if the data is of a size epsilon, then you can solve the equation for exponential time, e to the 1 over epsilon time. And the wave remains small and smooth for that period of time and decay like 1 over square root t. Okay. And in 3D, we have a similar result that because your decay rate is better, you can solve for longer time. So for example, if your data is of size epsilon, and you can solve for all the time, and the wave decay like 1 over t, and the wave remains small and smooth. Okay. So the key point is really for the 2D and the 3D water wave, the reason we can solve for so long is that we have a change of coordinates. Okay. So if you find, so for a certain good quantity, that's the projection of the height function into the space of holomorphic functions in the air region. And that quantity satisfies equation without an inappropriate coordinate system. So I'm not going to talk about it. So if you do a change of coordinate and you do a change of variable, then together you bring to such an equation, this equation has no quadratic nonlinearity. So that means through the right quantity in the right coordinates, your equation is more linear. So it obeys more linear behavior. And we know for linear equation, you can solve for all time. For nonlinear equation, the linear remains dominant for a longer time because you don't have the quadratic term. Here, it's important we are talking about small data, okay, small solution. So the quadratic is bigger than cubic, right? Epsilon square is bigger than epsilon cube. So if there's no epsilon square, the linear part is really, the nonlinear part is smaller, and you can solve for longer. Yeah?
Alpha is going
Yes. No, it's important. It's not Schrödinger. That's right. But in fact, you cannot reverse it. So if you reverse it, if you just look at this one, this is actually ill-post. This one is ill-post. So it's important that this theta is holomorphic in the air region. That restricted into become well-post. Okay. This theta is do not have positive Fourier modes. This is well-post. It's not like Schrödinger. It's actually exactly the opposite. It is a dispersive equation, but the dispersion relation is different from the Schrödinger. So this is really the equation look like. Okay, so of course it's not looking like this, but I'm writing like this. This is, in fact, the way I have written like here, it's really nonlinear. It's not linear. Okay, it's because this theta satisfies the Hilbert transform of theta, and Hilbert transform of a function theta depend on the free surface. The free surface is in the bottom. Okay, so this is still this is really a nonlinear operator. Okay, so there's a nonlinearity embedded here, but if you understand it, it doesn't bother you. It's actually, you can, if you really keep in mind this is your relation, you can work it out like it's linear. Okay, right? So it's not Schrödinger, and also the dispersion relation. So with this one, the dispersion relation is, so it's like omega of k equals to square root of k, right? So this is the group velocity will be like 1 over square root of k. So the larger frequency wave will stay, and the smaller frequency will just, which one will stay? The small, so the k is a frequency, right? So k, if the k is smaller, then the group velocity is larger, so it will go out. Okay, the small frequency wave will go out. The large frequency wave will stay. Okay, so it will just, the bad things will be in front of you all the time. The smoother wave will go out. Okay, move out. So in fact, it's important. This relation makes it very important what type of data you're dealing with. Okay, so if you have too many small frequency waves, in fact, even though you think this is a smooth thing, it's good for you, but too many small frequency waves, in fact, is not so good for the water wave equation. Okay, because it will just move to the far field very quickly, will make the decay rate not as good as it should be. So it's harder to work on. Okay. So I mentioned a few other work also. So this is for 2D, we have almost global. For 3D, we have global for small data and with different decay rates, right? So the reason is the 2D decays slower than 3D, okay? And the idea is similar. So precisely what we have is for 2D, we need initial height is small and the slope is small. But for 3D, we only need the slope is small. We don't need the height is small. Okay, so it remains we are still working, this is working with my former student, whether we can remove the smallness assumption on the initial height and initial energy. So this is really, the extra assumption on the initial height is really we don't want to have too many small frequency waves. Okay, so there are a few other work. So Germain, Masmoudi, Chattah has a different proof for the 3D water wave and for a different class of data. Okay. So in particular, their data specifies that there shouldn't be too many small frequency waves. Okay. So they have an assumption that the small frequency wave shouldn't be that much. Okay. And they have, for that case, they have also linear scattering. And this more recent work of Al-Azhar Dalal and Ionescu, Pusateri, and so actually I'm not mentioning it. This is like just last month, the Ifrin and Tataru, they can prove global existence for 2D as well by just, the extra thing they do is really understand the behavior of the cubic term. Okay, so they find the cubic term is not bad and they can solve for all time. Okay, so I will not specify, just say that, well, Ionescu, Pusateri has has to require the data satisfy additional moment condition. That means they have to put a small restriction on the amount of small frequency wave there. Okay. But Al-Azhar law has, in terms of data, is better in that sense. Okay. So their data is they assume the initial energy and height small, no extra moment condition. Okay. Okay. So these are what we know, and we also have so for the singularity, we have the work of, so let me just mention the work of Al-Azhar, Burke, and Zurli. And they basically, so the question now is, how do we understand the singularity, right? So the previous work all basically didn't really think too much about bringing the regularity of the surface down. Say, suppose we have such a wave, right? And it looks like it's not that smooth. Is this a well-posted situation, right? So what does happen? So does the water wave equation really describe such a behavior? Is this an admissible solution, say, for the case where there's no wind or any other effect? Okay. And so this is the work of Cordoba-Pfefferman group. Okay. And they show that there is a smooth wave that becomes self-intersecting at a later time. Okay, but there's more work developing now, and I don't think I will talk about it. I'm not the one to talk about it. Okay, so let me just emphasize the work of Al-Azhar, Burke, Zurli. Okay, so they can bring down the regularity of the surface to 3/2, around 3/2, and it used to be plus a little bit. Now they can minus a little bit. Okay. So minus a little bit by incorporating strict cost inequality. Okay. So, but basically, the situation they work on is the bottom has to be strictly away from the top. Okay. And this has to hold. Okay. So in all the work I mentioned is it's important that the bottom doesn't interact with the free surface, and this is strictly positive. Okay. It's greater than strictly bounded from 0. Okay. And of course, if you look at this picture, you would think that it's not 3/2, right? It looks like it should be worse than 3/2. Okay. For example, yeah. I don't know, right? I will tell you. Okay. So let's see. So let me turn this off. Okay. So let me turn this off so you will not remember the picture, and I'll show you later. See if you, or maybe I show that. Okay. So that's okay. Okay. So we continue with interaction. Okay. Interaction of the free surface with the bottom. Okay, so this is what we are concerned about. Okay, but of course with this angle, I mean, if you start with this, you probably get lost very quickly. So let's try to make our life a little bit easier. So suppose we just have a vertical wall. Okay, suppose our wall is just vertical, and of course you can put another wall here. Okay, if you like. Of course you don't have to. So you have another wall here. Okay. Okay, and let's just forget about bottom, right? You can always put the bottom there. Actually, the bottom in this distance to there will not interfere with the free surface. Will not add difficulty. So it's only at complexity, and for the moment we don't care about that. Okay, so we want to focus. Let's say, how does the wave interact with the wall? Okay, so now suppose I have okay, so suppose this wave makes an angle. Suppose this wave makes, say, a 90-degree angle with the wall. Okay. Okay, so let's try to understand what is the velocity on the wall. So we know that the velocity field is V1, V2, right? So if this is a vertical wall, that means the velocity V1 is always 0 on gamma. Okay? So that means you can make a Schwarz reflection. Okay? So make a Schwarz reflection. Okay? You can just make the wave. So if you make a Schwarz reflection, So you have wave coming in, and then you go like this, right? So the reflection is Vxy equals to V1 minus x minus V1 minus xy. And it's very easy to check that's still a solution if you make something like that. You just think about it goes like this, right, symmetrically. So you can make your life easier just by reflect it, okay? So if this is 90 degrees, so you reflect it, you basically are just really treating a smooth wave still, right, if it's 90 degrees. You reflect, it's nice, smooth, so it's not new, right? If we have a 90 degree, there's nothing new. It's really just not very interesting for us, okay? So the question is really that, is it possible to make a degree other than 90, okay? So this mu, does it have to be, what's a degree, okay? Can mu be not equal to pi over 2? That's the question, okay? Okay, can this angle be not pi over 2? So if I just do like a reflection, okay, so this is the same mu, okay. Can this angle be not equal to pi over 2, okay? And of course, we know that we can always reflect it, right? Keep reflecting like this. And everything in this, we know that the wave go up, okay? So there's really no complexity, right? You can reflect about this wall as well, okay? You can reflect about this wall, and you go like this. So that means that will you allow a kink in the middle of the wave, okay? Okay, so what is really the difficulty involved with such an angle? Okay, so the first thing is, of course, that, okay, so we have seen this very important thing, right? Negative dPdN has to be strictly than constant to be well posed, okay? So now if you allow your wave make an angle, B, okay, so we know that, okay, so I think I have to go back a little bit. How do we solve the water wave equation? Okay, so I think I go back to the equation. So the work on the well-posedness always reduce, this is a free boundary problem, right? We cannot solve it directly. But if you just say that, well, you stand on the free surface, you will stay on the free surface for all time. So like if you stand on the Earth, you will move with the Earth. You will not understand, you will not feel the Earth is moving, right? So the same thing for the free surface. So we just reduce to an equation on the free surface, okay? So we let that, say Z equals to Z alpha T is the free surface in Lagrangian coordinate. Okay, so this means that if I take derivative to t, I get velocity. If I take two derivatives to t, I get acceleration. Okay, so now the Euler equation becomes that. So of course, I'm going to just stay in 2D. Okay, and for all our experience is that if we can understand 2D well, we can always extend it to 3D by, we have the tool, right, Clifford algebra to do that. So we are writing things in complex coordinates, okay. And the good thing about 2D is we have complex analysis to use, okay. Okay, so in complex coordinate, the gravity becomes negative I, right? So G, let's say, call it 1, okay? So this equation, the Euler becomes ZTT plus I. This I is a gravity, okay? So G is 1 here, okay? So we take the gravity equal to 1, and this is equal to minus gradient P, okay? So now P equal to 0 on the free surface means gradient P has to point in the normal direction, okay? So this is the direction of the gradient P. We don't know it's inside, outside. Let me just draw it. Okay, so gradient P, okay, like this. Okay, probably it should be inside. Okay, I think it should be inside. So, but let me just draw it like that. Okay, doesn't matter. Okay, so that means gradient P is perpendicular to the surface. So this means I can write the minus gradient P as negative dPdN times the times the normal, unit normal variable, unit normal vector, right? So we know that Z alpha is tangential vector, and I Z alpha is a normal vector. Okay, and I Z alpha actually precisely is outward normal. Okay, so we can precisely just write like this. Okay, okay, and we have shown that negative dPdN is positive, and that's a good news. Okay, so I just write this as IA Z alpha, and A is minus negative dPdN. 1 over Z alpha, and we know this is something strictly positive. Okay, so let's add for the smooth case. Okay, and of course we don't have a smooth case here because we can keep reflecting, and that means it's equivalent to say if you have a kink in, if you have angle wave in the middle of the ocean, or sometimes you don't have angle wave. Okay, so this is what kind of angled wave is there? So this is a free surface. Okay, and we also have that. So this is the first equation. And now let me just write down the equation for the velocity, right? We didn't use divergence curl equals 0. So divergence 0, curl equals 0 means the velocity bar is a holomorphic function. Okay, it satisfies Cauchy-Riemann equation. So that means Zt bar is boundary value. Zt bar is a velocity bar evaluated along the free surface. Okay, is a boundary value of a holomorphic function. And you can write it in terms of the Hilbert transform. Okay, so we know that Zt bar equal to the Hilbert transform of Zt bar plus a constant, which is precisely the average along the interface. So let me just not write. This is a constant. Okay, so this is a constant. That's the average. Okay, along the interface. Okay, along the interface gamma t. Okay, so that's the equation we want to solve, right? And the idea in our earlier work is that, well, that's the equation that's still fully nonlinear. We want to solve it. So the classical, so we just take one more derivative to the first equation. And turns out that if you take one more derivative in time, you get a quasi-linear equation. So, but of course, this is not straightforward, right? After many tries, we get to here. And it's not taking spatial derivative, but it's time derivative. Just one time derivative make it quasi-linear. So we can just take, and actually I would like to put a bar over everything, okay, minus I, and put this. Okay, so this becomes ZTTT. And this equal to minus IA Zt alpha bar and minus I AT Z alpha bar. Okay, and it turns out these two terms. Okay, so let me just bring them together. It's dt squared plus IA d alpha of Zt bar equal to minus I AT Z alpha. Right? Let me write it like this. And turns out the left-hand side is really the higher order term, and the right-hand side is the lower order term. Okay? And the reason is this is a lower order term. The reason is that really Zt bar is a holomorphic function. Okay? And you can use I minus h to measure how non-holomorphic it is. Okay? So, I mean, just forget about the constant, right? This can always, let's just say it's constant, 0. So you apply, say, I minus h to both sides. Okay? And I minus h IA AT Z alpha bar, okay, equal to I minus h of dt squared plus IA d alpha Zt bar. And this really is a commutator, okay, because we are taking derivatives, the constant just disappears. So this is really just a commutator, and we know commutator always is of lower order. Okay, so that means the right-hand side is lower order. And that's the main thing, right? That's really, you see, that was the equation appeared earlier, right? dt squared plus I d alpha, okay, A equal to 1 when the wave is very small. Okay. Okay, so now let's see where does the Taylor sign condition comes in, right? So why Taylor sign condition is so important. So this is a quasi-linear equation, right? We have to solve this. And we know that A is minus dPdN times 1 over Z alpha. Okay. Now, I d alpha acting on a holomorphic function really is equal to the normal derivative, okay, is the Dirichlet-Neumann operator, or in fact, it's really I, the alpha Hilbert transform of ZT. And that's a positive operator, right? Because this is really Green's identity, right? Normal derivative is a positive operator because if U is harmonic, okay, on the gamma, and we know the Green's identity, this is greater than 0, okay, in the omega, okay, x, and that's a non-negative operator. So this is a positive operator, okay? Now, if you have the coefficient strictly greater than a constant, then you get a hyperbolic equation, right? So because this is a hyperbolic, if we know that if A is greater than a constant, then this implies that, okay, so this implies that dt squared plus A times the normal derivative is hyperbolic, okay? And that's precisely how we get local well-posedness, okay? And that's why the Taylor-Sum condition is so important. You need to have a strictly lower bound to get local well-posedness. So if it becomes negative, it's ill-posed, right? Okay. Okay, so this is an old thing, right? So now let's see what if the angle is not pi, okay? Or what if there's a kink in the middle of the wave, right? So suppose your wave, you can also think about your wave is looking like this, right? There's a certain angle like the graph, like the picture, okay? So what if there's some kink? So if there's some kink, so now let's just go back. So can I erase the board? Okay. So if I go back to the two main equation, okay? So this is our equation, right? So I keep it here. ZTT plus I is IA Z alpha, okay? ZT bar is H ZT bar plus a constant, okay? And which is the average, okay? Okay, so we know A is real valued, okay? A is minus dPdN 1 over Z alpha, which is real valued. So this means that Z alpha bar times ZTT plus I would equal to IA Z alpha square, which is purely imaginary, okay? So that means the real part is 0, right? So this means that the real part is 0, okay? X alpha, XTT plus Y alpha, YTT plus 1 equal to 0. Or you can say that minus X alpha divided by Y alpha is XTT, YTT plus 1. Okay. Okay, so now let's look at this angle, right? So this is a X alpha, Y alpha direction, okay? So this means that this would be, the vector field. So so Y is positive pointing out, right? X is like this. Okay, so this is the tangential vector field. Okay, so if I want to calculate this angle, I exactly equal to minus X of alpha divided by Y alpha. That would be tangent of mu, right? Okay, so this would be the tangent of mu. Now, what do we know about the velocity along this wall, right? So we know that the velocity on this wall, we call it gamma, right? So, of course, when it's reflected, it's still gamma. Okay, so we know the velocity on gamma, the velocity field is the tangential velocity is 0, right? The tangential part is 0. That means tangential is xt, right? So that means xt is 0 on gamma. And, of course, the fluid particle just moves up and down like this. If you take one more derivative t, it's still 0, right? xtt is also 0 on gamma. Okay. So this means that at this point, xtt is 0. Okay. xtt 0 is 0. So xtt is 0. So this means that, well, if ytt is not equal to 0, the angle has to be 90 degrees, right? So that means xtt equals 0 at the corner. Now, case 1 is if ytt plus 1 is not equal to 0, this implies that the angle mu has to be pi over 2. And that's the case we don't really care about, right? Because this falls into the previous result, okay? So now if we want the angle not equal to 0, not equal to pi over 2, that means ytt plus 1 has to be 0. So this means that ztt plus I has to be 0, right? And remember, that was gradient P, okay? Okay, so this means that gradient P has to be equal 0 at the corner. Or you can say that the PDN has to be 0 at the corner. Okay. Okay, so this means that, and actually you can do the similar calculation. We can prove it precisely. If you have an angle like this, everywhere on the angle, if you have angled wave, everywhere at the tip of the angle, negative dPdN has to be 0. Okay, negative dPdN has to be 0. Okay, or in other words, this equation becomes degenerate, right? And of course, we still have to prove if A is positive or not, okay? And which actually we can prove it's positive, non-negative, but it can become 0, okay? So if you involve such a singularity, negative dPdN is equal to 0 sometime. So that means you would have to deal with a degenerate hyperbolic equation, okay? So the question is this still well posed? Okay. I still have some time, right? Okay. Okay, so this is the first difficulty, right? This is really the main difficulty. So the negative dPdN become degenerate at the singularity. Okay. So first difficulty is, okay, first that minus dPdN equals to 0 at the singularity, at the corner, at the non-trivial corner, and at the angled crest. Okay. And the second difficulty is, of course, we want to build. So the first idea is, of course, we try to say, well, whether we can get a Prodi estimate, right? Whether we can get a Prodi estimate. Whether we can get a Prodi estimate. So to get a Prodi estimate, very often that we would like to take derivative to the equation. Okay, so we would like to take derivative to the equation to get some higher order energy. Okay, so now if I take derivative to the velocity field, okay, so we have this periodic domain, right? Actually, this periodic domain is not so bad. The periodic domain says that you see the velocity field has some probably. The velocity field only going up and down along the two walls, right, because we reflect it, okay, along the two walls. So this wall, we just disappear, okay, so just make it disappear like this, okay, because we just look at the reflected domain, okay. And in this symmetric domain, then, that velocity is up and down, simultaneous like this, okay. So we know that V minus 1 plus Iy is always V1 plus Iy. So this is periodic. Okay, so in other words, the velocity field is periodic. And we know that when we do the energy estimate, we have to do integration by part, right? In periodic boundary is good for us. But if we take, so the T-bar is periodic. But if I take derivative just straightforwardly to the spatial derivative, that's not periodic anymore, right? Because this turns the xt alpha, yt alpha, and because xt is odd, yt is even, so xt alpha is even, but yt alpha is odd, but it doesn't have to be 0 on the boundary. So this is not periodic. It is not periodic. But actually, this difficulty really points to us the right kind of quantity we should deal with, right? So this guy is not periodic, but something else is. So instead of taking derivative to d alpha, instead, so we know that V bar is holomorphic and periodic. So if I take the spatial derivative, we know that's the same as, because holomorphic, it's the same as like taking the y derivative, right? But y derivatives like this keep the periodicity, okay? So keep the periodicity, okay? Is periodic. Okay, so now if we look at this guy, we know that what is Vz? Okay, so we know that Zt bar is the velocity field evaluated along the interface. So if I just take one more derivative to alpha, I get Vz, and Z alpha. So this means that if I deal with this quantity equal to D alpha, Z alpha, that will keep the periodicity. Okay, so we just work on D alpha of this equal to derivative normalized by a complex weight. Okay, so this is the function we have to deal. This keeps the periodicity. Okay, keeps periodicity and holomorphicity, right? Okay, so instead of working on this, we work on d alpha zt and its many derivatives, okay, because this is a holomorphic in the periodic function. Okay, okay, so maybe let me just state result first, and okay, let me state the result first. So the result is this is a well-posed problem, okay, with even kinks in front of it. So the theorem is that there are two parts. The first part is joint with my student Rafe Kinsey. Okay, so this is the first part with Rafe Kinsey. Okay, so for water waves with angled crest, so that means the wave can have kink in the middle, and this angle, there can also be angle at the corner, okay, and also can have angles like this, okay, so like this, okay, and there is a energy. We can build energy E that's strictly positive, non-negative, okay, such that the energy actually satisfies such a ground wall inequality. Okay, so this P is a universal polynomial. Okay, and it doesn't depend on negative dp in the lower bound of negative dpdn. It's just with some constant coefficient. Okay, so actually the first result is with Rafe Kinsey as well. Negative dpdn is always greater than equal to 0, okay, and negative dpdn equal to 0 at the singularities. Okay. Now with singularity, with negative dpdn greater than 0 only, we can build the energy functional so that the energy functional satisfies such an inequality. So that means if the initial energy is finite, it remains finite for a short period of time. And the second part is there's a local well-posedness, okay, local existence in the energy space. Okay, so now, of course, by now you probably are very curious, what can we deal with, right? So in fact, it's worthwhile to say, so I think I will follow, I still have 2 minutes maybe? Okay, so it's important to say that, okay, so what could be the angle? In fact, everything can be derived from the equation, right? So this is, this is really, when you didn't look at it, so this is a water wave equation. Plus I is IA Z alpha. Okay. So if I take multiply Z alpha, I get IA Z alpha square. And of course, classically, the first paper we had was that we proved this quantity. So in fact, in Riemannian coordinate, okay, in Riemann coordinate, we write like this. I don't go to the detail, and we can talk afterwards. In Riemann coordinate, this is after Riemann mapping, okay. After Riemann mapping, okay, or in Riemannian coordinates, okay, we have that A1 is greater than equal to 0. Now this one, Z alpha, is really the inverse Riemann mapping. So this means that this is your wave, okay, and you get Riemann mapping, okay, into flat, right? But inverse Riemann mapping, so of course if you have an angle here, okay, and you can look at, so the inverse Riemann mapping is capital Z. Okay, capital Z is inverse Riemann mapping. So you can figure out what is this Riemann mapping. This is like Z, and it has to change the corner, right? So this means that inverse Riemann mapping, so if suppose this is 0, right? Sorry, it maps to here, okay? This is 0, okay? And this angle is mu. Then inverse Riemann mapping should behave like Z to the R, okay? And R times pi over 2. So R takes pi over 2 to mu, okay? To mu, the angle nu. R takes nu. Okay, so that's what you get. Okay, now you can look at this relation. So A1 is actually greater than or equal to 1. That's what we can prove. So that means 1 over Z alpha is IA1 divided by, so it's ZTT plus I divided by I is A1. Right. With a bar somewhere. Okay. Minus with a minus sign. Okay, so somewhere's minus or plus, okay? Okay, so now if you look at this relation, you will see that if you just look at this relation, because 1 over Z alpha directly relates to the Riemann mapping, and you can figure out that actually this is all with Rafe-Kinsey, right? So only this part is without Rafe-Kinsey. So let me write this is part 3, okay? And part 2, and also that, okay, part 2 is what we can say is this angle mu has to be less than or equal to pi over 2. This is all derived from this water wave equation. So that means you will never see a wave like this. Okay, this angle cannot be over pi. Okay, this is wrong. Okay, you can only see wave like this. Okay, but now with our energy, okay, mu has to be less than or equal to pi over 2. But with our energy, actually, with this energy allows angle mu less than pi over 4. Okay, so in fact, your angle has to be very steep or it's flat. Okay, and I just mentioned that this is exactly the same angle as some earlier work we get from the self-similar solution. Okay, so I did construct a self-similar solution. I was also thinking about this one. Okay, and I was thinking, can we use self-similarity to describe it? And the self-similarity also shows that the wave should look like this, okay? And this angle mu pi has to less than pi over 2, okay? And that's exactly the same as the energy we built. The energy allows pi over 2, but not bigger than pi over 2. But definitely the equation really rule out this completely. This is ruled out by the equation, and this is admitted by energy. Okay. And this is really ruled out by equation. Okay, I think I stop here. Thank you.
Are there some questions?